Hello, everyone. Welcome. Uh, was not hoping to do any video lectures this semester, but I am sick, and I wanted to keep you all healthy. So let us do this. I hope you are indeed doing well. I'm hoping I'll be better by Wednesday. If not, you'll get another video. We'll see. But what we've been talking about here is groups, and a group is just our attempt to sort of distill down the idea of a binary operation, which is the central thing that we're studying in algebra, to its sort of simplest form. And so, in order to get a group, you have to have a set with a binary operation. Remember that as soon as you have a set with a binary operation, that means the binary operation has to be closed. You're not allowed to multiply two elements of a group and get something outside the group. You have to always get something, and that something always has to be in the group. Uh, and then we have a few other requirements. One of them is that it has to be associative. Now, this is interesting because, on the one hand, it's very difficult to be associative because if you think about it, what does it mean to be associative? It means for every x, y, z, these two random strings involving x, y, and z happen to be equal to each other. That's something that's very unlikely to happen. So the fact that we have anything that's associative at all is kind of miraculous. But on the other hand, almost no one wants to spend any time thinking about an operation that's not, in fact, actually associative. And so this is a requirement you're very rarely going to see sort of go missing. Next is we need to have an identity element, something that you can multiply every element of the group by and get that element of the group back. And last, and this is the one that's given us the most problems when we've went through familiar examples, is that every element of the group has to have an inverse. And so a lot of the weird things we've done to come up with examples of groups have been dealing with the fact that some things naturally don't have an inverse, and so we throw them away and then get something where it does work. I'll remind you of that in a moment. Lastly, I wanted to note a really natural requirement for an operation would be that it's commutative. That is, that x star y and y star x are always the same. We emphatically don't insist on that for a group, but we do give a special name to groups that do have that property. Namely, we call them abelian groups. Now, you might rightly have the question, why on earth don't we call them commutative groups? Wouldn't that be easier? And the answer is yes, that would be easier, but we call them abelian groups anyway. Who knows? Algebraists love words for things. Okay. Real quick, just so that you have it all in one place, I wanted to go over our examples of things that are groups. So the integers, the rationals, the reals, the complex numbers. All of these are groups under addition. I'm also going to sneak Zn in here. Remember that the addition in Zn is mod n. So that's an important note. But these are a familiar cast of groups with the operation of addition. Examples with multiplication is where it turned out that because of the need to cater to inverses, we usually had to do something weird. So when we started with the integers, actually, by the time we stripped away everything, we actually got left with this really funky two-element group that only had 1 and -1 in it. It is a group, but it's, in some sense, not a very interesting one because it only has two elements. All three of these, we needed to throw out only 0. So those gave us the groups Q cross, R cross, and C cross. In those cases, the only thing we threw out is 0. And then everything worked out okay. We also talked about this Zn cross, which is a rather weird version because here we remove everything that shares a prime factor with n. So for example, if you were to write down Z9 cross, it would include 1 and 2, but not 3, because 3 is a factor of 9. It would include 4 and 5, but not 6, because 6 and 9 share the prime factor of 3, and 7 and 8. Remember, I just outright abolished 0 from it, although if you really boil down and decide what numbers divide 0, you'll eventually decide with great regret that every number divides 0. But it's probably better to not think about that, and so not think about sharing prime factors with 0 at all, and just always kick 0 out. Okay. Again, this Zn cross, it's always a group for n bigger than 1. And it's a somewhat unpredictable group, at least based on what we know so far. So, for example, this one for Z9, we ended up with, it looks like 6 elements, but you never quite know what you're going to get with this group. But it is a group under multiplication mod n. So again, just to make sure we understand it, if you multiply 4 and 5 in this group, you get 20 mod 9, which is 2. We haven't really talked much about matrices, and we're not honestly going to talk an enormous amount about matrices, but I did want to tell you just a little bit of a story about how these things work with matrices. So if I take MNR, that's just my notation for the n by n matrices over the reals. This is a group under addition. If I add two n by n matrices, I indeed get an n by n matrix, and I satisfy all of the identities, the zero matrix, and inverses, all that good stuff. Okay, so this is a group under addition. I'll note this also works if you replace the R here with any other place where you know how to add and multiply. So you might, for example, think about something like MNZ, or you might think MNZ11, et cetera, et cetera. There are a whole lot of options for what you can do here that will give you other groups, but they're still groups under addition. Now, what about multiplication? Are n by n matrices going to be a group under multiplication? Well, first thing to check is make sure that if you multiply an n by n matrix by another n by n matrix, you get an n by n matrix, which is true, and is why I insisted on staying with square matrices for this discussion. If instead of sticking with square matrices, we allowed like 2 by 3 matrices, then when you multiply two by 3 matrices together, you either don't get anything, or you get a 2 by 2 or a 3 by 3 matrix, neither of which is the right kind of flavor of thing. So in order to sort of stick in our comfortable, familiar binary operation land, we need to only be multiplying n by n matrices. But then the question that befalls us is it true that every matrix has an inverse? And now, if you have had 240 before, at this point you probably have flashbacks, because there's this whole giant thing called the invertible matrix theorem. And indeed, probably about half the course was about the fact that half of matrices don't have inverses, or some amount of matrices don't have inverses. So many matrices don't have inverses. The really easy way to tell, by the way, if you have a matrix and you want to know if it has an inverse or not, take its determinant. If its determinant has an inverse, then the matrix has an inverse. And if its determinant doesn't have an inverse, then it doesn't have an inverse. So, for example, if you're over the reals, that's saying if the determinant is 0, then it doesn't have an inverse. But if the determinant is literally anything else, then it does. So this immediately tells you in exactly the same way that R is not a group under multiplication because you can't divide by 0. 0 doesn't have an inverse. The n by n matrices are not a group under multiplication. What is a group under multiplication is this thing that we denote by GLNR. This is the general linear group. So this is the set of n by n invertible matrices. Okay. And this is a group. Now, if you looked back at our examples, you might come to the conclusion, especially after I introduced it at the beginning, that maybe all groups are going to turn out to be commutative anyway. Maybe they were all going to be abelian groups, because every example that I listed up until now, all of these and all of these, every single one of them was commutative. Even the n by n matrices under addition are commutative. However, the n by n invertible matrices under multiplication, they are not commutative. So this is your go-to example for now, and I'll give you another one by the end of the video. But this can be your go-to example of a non-abelian group. All right. So that is about all of the examples of groups I can harvest out of things that you've already seen before. But there are a few more groups that I want to introduce you to that you probably haven't thought about before. And so these are great examples to have in the back of your pocket, particularly because a lot of the homework questions ask you to think about like, hey, is this statement true? And often the sort of the thing that you hope for is that you'll realize, no, it's not true because I already know an example where it's not true. It's great if that happens. This first group is a great example to go to for that. This is V4. This happens to be called the Klein 4 group. Okay. Now, why is it represented by a V? It's represented by a V because Klein was German, and so called this the Wehrgruppe. Wehr being the German word for 4, which starts with a V, so we get this. So now it's called the 4 group because it has 4 elements, and I'm going to call those E, A, B, and C. Now, notice, I have not yet described for you a group. The reason why I haven't yet described for you a group is that I haven't given you a binary operation. I haven't explained to you, if I hand you 2 of these things, how do you multiply them? Okay. So in order to be able to multiply them, I have to tell you a couple things. So the first is E is the identity. So in other words, E times A is A times E is A. E times B is B times E is B. E times C is C times E is C, and E times E is E times E is E, right? When I say it's the identity, I'm actually just making those statements. So that's like 8 equalities, I suppose, worth of information when I just tell you that. Second, I'm going to tell you that if you multiply any element by itself, you always get E. So in other words, I am telling you E squared, which I've already told you, but also A squared, B squared, and C squared are all E. Okay, and so lastly, I have to tell you what happens if you multiply 2 things together and neither of them is E, and they're not the same. So if you multiply 2 distinct elements of A, B, C together, then what do you get? You get the third one. So A times B is C, B times C is A, C times A is B. However you want to do it, any 2 elements you multiply together out of this ABC set, if they're the same, I've already told you how to multiply them, and if they're different, you get the third one. Now, one thing I want to point out is if your group is small, like this group, you can actually define the operation by giving a complete table that tells you, for every pair, what do you get? And so I'm going to do that for you really quick here. So the first rule I told you is that E times everything is the everything. So E times E is E, A, B, C. And then going down the other way, A, B, C. Everything times itself is E. That's describing the cells that are running down this diagonal. A times B, that's supposed to be C. A times C, that's supposed to be B, because remember, it's the other one. B times A, that's supposed to be C. B times C, that's supposed to be A. C times A, that's supposed to be B. And C times B, that's supposed to be A. So if you didn't like my sort of ad hoc, this is how you multiply it based on what things there are, this is just a complete list of how everything multiplies together. Now, you can just take my word for it. V4 is a group. Now, most of that is very easy to check. So it has an identity element very explicitly because I sort of worked it in. I even defined E basically to be an identity element. So great there. It's definitely a binary operation. In this table, all that's really saying is that the only things that appear in this table are E's, A's, B's, and C's. That's great. Does everything have an inverse? Well, yes. In fact, everything's inverse is itself. So A, what do I multiply it by to get the identity? It's A. And then B, I multiply by B to get the identity. C, I multiply by C to get the identity. So everything is its own inverse. The only thing that's kind of annoying to check is associativity. So we're just not going to. You're just going to probably believe me. But associativity is often the one that's really annoying. So, for example, this is a slight tangent. The area of research I work in is elliptic curves. We talk about that some in number theory if you're very interested. But elliptic curves, they are groups. And the way it works, almost every part of proving that they form a group is very easy. However, proving that they're associative is a multi-day proof. So these are the sorts of things that often come up when you go to try and prove something's associative. It will often turn out to be more difficult than you had perhaps bargained for. So just buyer beware. Okay. I want to talk about two more examples. So one of them is Q8. So this is called the quaternion group. And so the elements of this are plus and minus 1, plus and minus I, plus and minus j, and plus and minus k. So note, there are 8 total elements. This group, we're going to define how it works by noting several things like we did for the first one. So the first is 1 is the identity. So if you multiply 1 by anything, you get that anything. The second thing is that minus signs work the way you think. By which I mean if I multiply two things with minus signs in them, the minuses go away. And if I multiply one thing with a minus with one thing without a minus, then I'm left with a minus. All right, so those pieces are here. Now, the I is perhaps suggestive of what I'm going to say I is, because I'm going to say that I squared is minus 1. So if you want, you can think of I as being this sort of friend from the complex numbers. But we're also actually going to say that j and k also share this property. So I, j, and k all square to be minus 1. Okay, and lastly, I'm going to show you this little multiplication Ouroboros that might look familiar if you've thought much about cross products. Because if you've thought about cross products, which is this thing to do with three-dimensional vectors that you probably would have done in something like vector calculus, you might have learned that if you do multiply the vector I by the vector j, then you're going to get the vector k. But then there's this weird trick of if you multiply the vector j by the vector I, you actually get minus k instead. And so you might have learned this little mnemonic to help you know what you get. So let me just show you how it works. If I multiply and I match the arrows, I just get the next thing. So I times j is k, j times k is I, and k times I is j. However, if I screw it up and I go backwards, then I get a minus sign. So j times I is minus k times j is minus I, and I times k is minus j. So this is our quaternion group. And so just, again, to be clear, if I took minus j times k, what would happen? I'd say, okay, well, j times k is I. So this will be minus I, for example. The minus will just hang out and give me a minus up front. Okay. Again, any group that has only a very small number of elements is hugely advantageous when you're thinking about this because they're super concrete. And so they're easy to work with. So this in particular, this is a great group to have laying around as an example to sort of beckon from when we talk about things in the future. I'm going to define for you one other small group. It's going to be, and now here I have to make a choice. I'm going to call it D8. And this is the set of symmetries of a square under composition. So what on earth does that mean? Well, here's my square. Imagine that there aren't lines on it, but I'll just go ahead and just to make my life easy, I'll label the corners. If this were a completely plain square, and I were to turn my back and you were here, you could do a lot of things to this square that I would not be able to tell. So for example, you could rotate it by 90 degrees. And if it weren't for these lines running across the top, it would look exactly the same. Rotate it by 180 degrees. If it's plain enough, you can even flip it over completely. Again, this is not a perfectly plain square, so you can actually see that I flipped it over. Any of these things you do, if the square is completely plain, it's indistinguishable. These things we call symmetries of the square. And we can actually sort of write out what are the symmetries of the square. And so let's make an agreement. So what are the symmetries? All right, so let's make a complete sentence here. So the first thing is one symmetry is just don't do anything at all. Just don't touch it. All right. The next is the one I described where I said rotate it 90 degrees clockwise. But if I'm going to do that, I could rotate it by 90 degrees clockwise twice, and that would be a different one. I'm going to call that r squared. And I could rotate it by 90 degrees clockwise 3 times. That would be r cubed. Now, you might think I could rotate it clockwise 4 times, which I can, but if I do, I've done the same amount of work as doing nothing. So I'm not going to count that as different from doing nothing. If 2 different ways of moving the square put the square in the same position anyway, I'm just going to count them as the same. And so for the same reason, I'm not going to list rotate the square 90 degrees counterclockwise, because rotating the square 90 degrees counterclockwise would do the same thing as rotating it 90 degrees clockwise 3 times. Namely, this is the same as that. That is what I am saying. Okay, so that's 4 elements so far. And now, interestingly enough, if my square was like the one I actually have in front of you, and the back of it was different from the front, this is actually the complete list of symmetries. There's nothing else I could do. I could only sort of rotate it. But because here I'm specifying a completely blank square, I also have to account for the fact that I can flip it over. And so I'm going to just draw a line down here. And so I'm going to make that F, we'll call that flip across the vertical axis. Okay. And so if I do F, then I have done that. Now, what if I do F twice? Well, then I'm going to come back to where I started, right? So I don't even actually have to write F squared. F by itself is just one of these symmetries. Now, of course, I can combine any of these things however I would like. So it's probably worth asking, how many total ways do I expect there to be to orient this square? That is, how many distinct ways do I expect to be able to arrange my square? And it might take you a bit to decide, but the answer is actually that there are 8 total, which is why, by the way, this was called D8, because it has 8 elements in it. So how do I decide that it's 8? Well, the first thing to do is decide what goes in this corner. And so I have, if you've looked here, I have 4 options for what goes in this corner. 1, 2, 3, or 4. So I could choose, say, 3, or I could choose 2, whatever you want. Okay. Now, the key thing to notice is as soon as I've chosen what goes in this corner, I no longer get a choice of what goes in this corner. Because the corners stay opposite no matter how I manipulate the square. I can't sort of tear the square in half and move this around. So now, once I've decided what goes at the top left, I've decided what goes at the bottom right without really having any choice. And now I just have to decide what to do with these 2. And there's two things I could do with them. I could leave them like this, or I could flip it upside down, while preserving, again, the top left and the bottom right, which I pinned down. And so there are two options. And so that means that in total, there are 4 times 2 symmetries. Now, I wrote that down so we'd know when we were done, because currently we've written down 5 symmetries. So nothing, r squared, r cubed, and f. But there's a few more that I can think of, which are fr, fr squared, and fr cubed, which all involve rotating and flipping the square in some combination. Now, for reasons that are incredibly technical and that you don't have to worry about, I'm always going to read these right to left instead of left to right. So I'm going to view this as, when I'm describing this element, I'm thinking of this as rotate 3 times, 2, 3, and then flip across this vertical axis. Likewise here, when I read this, I'm going to view this as rotate twice and then flip across the vertical axis. So that is how I am reading this, is reading them as sort of applying to the square from right to left. And so that's my D4's elements. And I've kind of already described for you what the group operation is. So let me write out the elements. So those are the 8 elements. And the group operation is to compose the symmetries. And just to be explicit, the operation is apply the symmetries in order from right to left. And so the thing here to keep in mind is that we're really claiming here, if I sort of apply 2 symmetries, then the thing I get is a symmetry. But that had better be the case, because otherwise my 2 situations weren't actually symmetric to start with. Now, I go over this example for a couple of reasons. One is this is just a cool group to have access to, and we'll use this a lot. This does generalize, by the way. I happened here to pick a square. If you did this with a pentagon instead, you'd have D10, and you'd have a very similar collection of things. D12, you'd start with a hexagon, and so on. But also, this speaks to where groups most naturally come up, which is that groups most naturally come up when thinking about symmetry. In some sense, Galois was the first person to think about group theory, although Galois died long before writing down the definition of a group. But Galois was thinking about groups in terms of symmetries of the roots of a polynomial. And so if you think back to your LaTeX assignment, there was this bit about trying to find a formula for the roots of a quintic. What Galois realized was that this might actually be a problem in a weird way, in that he suspected there would be quintics where there were too many symmetries among the roots for this to be possible, for you to actually sort out all 5 of them. And Galois figured out a way to make precise the statement that this thing has too many symmetries. You cannot sort them out, and so there can't be a formula that sorts them out for you. If you want to think about it this way, even something like the reals under addition is secretly a symmetry when you describe something like adding 3. What is adding 3 doing to the real line? It's taking the real line and it's sliding everything down 3. And the thing you can notice is, hey, the real line looks the same after you slide everything down 3. Right. This connection to symmetry is why group theory shows up in both physics and chemistry, among other natural sciences where you'd think it had no right being. It's because all of those things care very much about symmetries. And so group theory is a natural way to study collections of symmetries. Okay, so I just really quickly wrote down for you 3 examples. The Klein 4 group, the quaternion group, and the dihedral group, which I'll note, by the way, every time I write this down, I'm going to pause, because half of the people in the world would call this D4. No one agrees whether they should call it D sub the number of elements or D sub the number of sides on the shape. So I'm going with the number of elements in this class, but I'm going to have to think about it every single time. Let's ask, which of these are abelian? So V4, we wrote out this whole table for. And I want to point out this table actually lets you see visibly that V4 is abelian. And the way you can do that is if you think about what does it mean in this table that A times B is equal to B times A, it actually means that if you flip the entire table along this diagonal axis, you should get the same thing on both sides. So abelianicity, if you like, is really just the statement that these entries mirror themselves exactly down to here, which they do. So V4 is abelian. Q8, I've actually given you enough to know fairly easily Q8 is not abelian because I times J and J times I are different. I times J is K, J times I is minus K. So Q8 is non-abelian. D4, it's a little trickier. So let's try and understand what happens if I do RF versus if I do FR. And in order to try and understand this, I'm going to label the backs of the sticky sheet as well. So there's 1, that's 2, that's 3, and that's 4. So if I do F and then R, then I end up in this exact orientation, which I'm just going to copy down. What happens is I end up here. I end up with a 3, 2, 1, 4. If, however, I do R and then F, I end up in the position 1, 4, 3, 2. And these two are different. So these are not equal. And therefore, that tells me D8 is non-abelian. Thank you, prop square. Okay. Last today, I wanted to give you a couple little results that you can quote about things that are true of all groups. So the first is what we'll call the cancellation proposition. So this says that if A, B, and C are elements of a group, and A times B equals A times C, then B equals C. You can actually think about that very specifically in terms of what it's saying about one of these tables. It's saying that if you look at a row of one of these multiplication tables, there are no repeated entries. Because if there were repeated entries, then it would be possible to write down a B and a C here that were different. Okay. Now, of course, the proposition is equally true if we flip it around. So if B times A equals C times A, then B equals C. And that then is the statement that the same is true of the columns. The columns have no repeated entries. And so if you want to think about it this way, what this is basically saying is that this is something like a Sudoku box, where everything that shows up in the table only shows up once in each row and column. Okay. So I should take a second to convince you that this is actually true. So let's actually suppose that A times B equals A times C. And let's try and use nothing but our axioms to prove that that's actually true. So, in other words, let's try and go back just to this list of properties, and let's try and convince ourselves that this implies that. Okay. So the first thing to note is A inverse exists. That's because everything in a group has an inverse. So A inverse, it's a perfectly cromulent element. And then what we're going to do is we're going to multiply both of these things by A inverse. Okay. Now, you might pause and ask yourself if we're really allowed to do that. But remember, we assumed these two are the same element. They have the same name. We just haven't written them in that way yet. So whatever that name is, we can just drop it here. And so definitely if I multiply A inverse by that thing, I'm going to get the same thing as if I multiply A inverse by that thing. Note the parentheses are here because I started with A times B and then I multiplied that quantity by A inverse. So this operation happened first. Likewise, that operation happened first. But now star is associative. And so what that means is that I can regroup my parentheses. So instead, right, this is A inverse times A times B equals A inverse times A times C. But now what does an inverse even mean? An inverse means that when you multiply it by A, you get the identity. So that says that E times B is equal to E times C. But what does it even mean to be an identity? The thing it means to be an identity is if you multiply something by it, you get that thing. And so by definition of identity, what I get here at the end is B equals C, which is the thing that I wanted to prove. Okay. So that is a very helpful thing. And so basically, what we described here in this proof is dividing both sides by A, which is a very familiar Algebra 1-y sort of thing to do to both sides of an equation. But note, it doesn't always work with numbers, right? So this statement here is not actually true for the real numbers, although you would not fall for it probably if you saw it in real life. Because, for example, 0 times 3 is equal to 0 times 7, even though 3 is not equal to 7. And that's okay, because there's no group under multiplication that contains these elements, because remember, 0 doesn't have an inverse. And so this proposition is not ever going to apply to something involving multiplying by 0, because multiplying by 0 is going to mean that 0 doesn't have an inverse. In fact, also, if you want to think about it this way, anything that acts like multiplying by 0, well, what would happen if my multiplication table involved an element that behaved like 0? Well, 0 times everything is supposed to be 0. So if I were to put a 0 into one of these, in quotation marks, groups, then I would add a whole row of zeros or a whole column of zeros. And if my goal is to have no repeats, putting a whole bunch of the same thing in a row is going to be really problematic. So that's just not going to work. Okay. So really what we've done here is we've actually captured when it works to divide both sides by the same element. Okay, a few other minor things that I want to do before we wrap up this section. First, what is x times y inverse? Okay. And our natural inclination as beings who have largely worked with commutative things is to guess that it is x inverse y inverse. However, that won't work if our thing is non-abelian. And let me show you again what we're trying to do. Remember, when we're trying to find the inverse of x times y, we're trying to figure out the thing we can multiply by x times y in order to get the identity. Well, that means I don't want an x inverse here. I want a y inverse here, because the y inverse will go next to the y. Those will cancel and give me the identity, and then they'll just disappear. And then I can have my x inverse. And so this whole thing just xylophones out of existence and gives me the identity like I want. So in fact, that tells me that the inverse of x times y is actually y inverse x inverse. You'll often hear this called the shoe sock principle. So the idea here is that x is put on your socks, y is put on your shoes. So if you do x, y, you put on your socks and then you put on your shoes. And then you want to undo that. You don't undo it by taking off your socks and then taking off your shoes. You undo it by taking off your shoes and then taking off your socks. And so that's a way of thinking about what is actually happening here. All right. We're going to wrap up today's lecture here. Again, I hope I'll be back Wednesday. Who knows? I'll keep you in the loop. If you have any questions about the homework in the meantime, definitely feel free to email me. And I hope to see you then. I hope you are all having a happy and healthy time with your semester so far. And I can't wait to see you all again. So have a wonderful day, and I hope to see you all very soon. Bye for now.